All right, welcome class to lecture 22, where we're going to continue our discussion of rare events and reactive processes. Today, we're going to focus on an application of this theory, which is one of the most celebrated applications of transition state theory, known as Marcus's theory of electron transfer. It's a very simple process that I think will help us elucidate this so far somewhat mysterious reaction coordinate, this Q that we've been plotting for energy surfaces along. And it'll help us understand, how one actually would apply this sort of theory in practice to a system where the mechanism is non-trivial. It's not just a bond dissociation event where you kind of understand that the reaction coordinate might just be a displacement along some bond axis. Before we get there, I want to reflect a little bit on where we've come in building up this theory of reaction rates. So we have, beginning a couple lectures ago, identified a microscopic way of computing a macroscopic reaction rate. If we imagine some process A goes to B, well, if we had a solution of A's and measured how long it takes to build up some concentration of B's, if this really was a first order reaction like I've written, there would be some macroscopic law, some macroscopic time scale associated with the increase in concentration of B. To the extent I can imagine that A's and B's are independent, that would reflect an underlying microscopic process that is actually converting A to B. And we have figured out exactly how to calculate that rate. It is given by, in one realization of the equation, the flux through some transition state, denoted by Q star, given that trajectory eventually ends up in state B, times the probability to have gotten to that transition state, provided you started in A. So the picture we keep drawing is some sort of double well where two metastable states are distinguished along this variable Q. That saddle point exists at Q star. And the rate then is the probability that you have a spontaneous fluctuation that brings you to the top of that barrier. The flux over that barrier, given you end up reacting. So in the equation, this Q dot is the flux, the rate of change of Q, it is conditioned to start at the top of the barrier and end in B at time t. And this exponential, that Boltzmann factor, divided by L, L being a characteristic number of states or width of that basin, encodes the probability of getting to Q star from basin A, distinguished from basin B through this dividing surface at Q star. So to the extent that the rate is a rare event, that there's a separation of timescales between a local equilibration within one of the basins and the reactive event, this expression then is exact. So essentially, as long as that rate exists, this is an exact way to compute it. However, that expression is a time correlation function. It requires knowing how the flux at 0 is correlated with committing to be a time t later. An approximation to that, which neglects all of those dynamics, is transition state theory, which boils that calculation of a rate into a calculation of a few thermodynamic quantities. So the transition state theory estimate of the rate is just the flux at 0 times the probability it was going in the right direction. If it really is a flux, then it's an even variable in equilibrium. The likelihood it's going left to right is just 1/2. And then I keep these factors of the probability of getting to the top of the transition state. That is an approximation. In that it neglects the dynamics at the top of the barrier, and specifically neglects potential recrossing events that starts the dynamics going in the right way to commit to B, but turns them around due to a fluctuation in some orthogonal degree of freedom, or that finds the system evolving towards state A through the dividing surface, but gets turned around and eventually does commit to basin B. So these were the initial findings of our discussion on rates. Most recently, we discussed how to correct transition state theory through the calculation or study of the so-called transmission coefficient, often denoted kappa, which is just defined as the rate in its full glory divided by the transition state theory estimate. The factors of the probability to get to the top of the basin cancel. So it's just this ratio of the time correlation function that enters into the rate divided by its 0 value. And most recently, we worked out a couple different theories. So first, this is something bounded from above by 1. Correlation function is strictly decaying from, is decaying from 0. Transmission coefficient could oscillate. So we worked out a couple theories for this that are notable. From Kramers, for example, one could imagine or model the dynamics at the top of the barrier through an overdamped equation of motion. Imagine that the reaction is proceeded in a viscous environment, resulting in what is known as the spatial diffusion limit, in which case kappa goes inversely proportional to that friction, which is another way of saying it goes proportional to the diffusion constant at the top of the barrier. Hence the name spatial diffusion limit, because you really are just waiting for the dynamics in the Q degree of freedom in this spatial coordinate to evolve to commit the system to the B basin. An alternative limit is in the underdamped limit, in which case one is not waiting for the particle to move spatially, but rather for its energy to be lost to the environment. So when the coupling to the bath is very small, the rate limiting step to commit is just the likelihood that the bath acts on the system to actually reduce its energy, to allow it to relax. The rate of relaxation due to energy transfer to the surroundings goes like the friction, and thus kappa scales in proportion to gamma directly. leading to what we noted last lecture, the famous Cramer's turnover, the non-monotonic dependence of the transmission coefficient on kappa, observed in lots of different sorts of systems as you tune the viscosity, or as other orthogonal degrees of freedom become more or less correlated with the reaction coordinate. Finally, both of those examples assume that the bath, while maybe interacting strongly or weakly, does equilibrate quickly. And thus, these are both Markovian approximations to kappa. A non-Markovian theory for the dynamics at the top of the barrier comes from Grote and Hines. In which case, kappa turns out to go like a ratio of the frequency at the top of the barrier in the denominator of a ratio that depends on the so-called Grote-Hines frequency. Which is essentially the frequency, the resonance frequency for which the bath memory kernel can most effectively act on the system evolving at the top of the barrier in order to commit it to the B basin. All right, so that's kind of where we've been. We have this framework for thinking about rates. We understand kind of the underlying statistical assumptions. We understand the underlying physical approximations that can be made to treat them. What we're going to do for the rest of the class is now apply transition state theory in a somewhat famous case, the case of electron transfer. So electron transfer reactions or oxidation reduction reactions are really significant processes in chemistry and biology, even physics. They're the simplest process by which a reaction can occur in some sense, in that no bonds are made or broken in the course of an electron transfer. Charge is just redistributed. So whether or not that charge is an electron hopping around in a solid state lattice or a set of metal centers undergoing redox chemistry in solution, Marcus's theory has widespread applications. We're going to envision the latter case, having in the back of our mind some process like an inorganic Ferrospheric exchange reaction, whereby in a polar solvent, like H2O, we have two redox states of some metal center, like iron. Maybe one comes in a 2+ state, and the other is in a 3+ state, so there is an extra electron on the 2+ state. Iron being the same there means that the electron energetically could reside either on the 2+ or 3+ metal center, and thus that electron you should expect to exchange over the course of those two species diffusing in solution. That exchange is the electron transfer event. So to give you a sense for the scales involved in a process like this, it's worthwhile noting some of the basic energetics associated with moving an electron from one site to another, or ripping it off and pulling it into the vacuum. In addition to the characteristic timescales over which we might expect some of this motion to proceed. Because again, in transition state theory, we assume that there are separations of timescales for that rate to be well defined. We need to be able to justify that in this case. So let's consider this so-called Ferrospheric reaction as a kind of concrete example that we can think through and try to understand. Okay, so first, energetically speaking, I'm taking an electron off of a 2+ iron center and depositing it back on an iron 3+. So what is the energy scale I should expect for that process? So if I ask in vacuum for the ionization energy, of iron 2+, what should we expect that basic scale to be? First, it's a positively charged metal center. It's not going to want to give up an electron, all things being equal, especially if I put that species, say, in the vacuum rather than H2O. If it was a hydrogen atom, we know what the ionization energy is for a hydrogen atom. That's the binding energy of the electron to the nuclear charge. That's atomic units. Essentially defines an atomic unit system. So it's something like a Hartree. Iron's a little bit bigger. It has more electrons. It might be a little more forgiving. If you go and look this up in a table, the ionization energy, the third ionization energy for an iron atom comes in at about 10 eV. Smaller than the ionization of a proton, but still much, much greater than kVt. In fact, if we just assume that that's the barrier over which the electron has to surmount to undergo this exchange reaction, what would we get? So transition state theory tells us that there is some flux, some characteristic attempt frequency for trying to surmount that barrier. The rate then is the product of that attempt frequency times the probability to get to the top of the barrier, which is Boltzmann distributed. So we have an ionization energy, typically measured in vacuum, of 10 eV. So that gives us the probability of overcoming that specific barrier, if that was the relevant barrier. Characteristic timescales of electron motion will give us a ballpark of what that attempt frequency is. Does anyone know what the characteristic timescale of an electron is? What a typical orbit time or frequency would be? Ballpark, you should think about attoseconds, 10 to the minus 18 seconds. So 1 over the rate, naively from transition state theory, would be that time scale times e to the beta e ionization. That's at 10 to the minus 18 seconds. 10 eV, well, 1 kBt at room temperature is 0.025 eV. All right, this is going to be absolutely enormous. The rate, or the characteristic timescale, so let's see, 10 divided by 0.025, so I have a 10 to the minus 18 here. I have, how many times does 0.025 go into 10? So it would go into there's about 40 in each in EV, which means that there's about 400. Converting from base E to base 10 gives me about a factor of 3. Ballpark, this is 10 to 150 seconds or so. That's much, much longer than the age of the universe. If the barrier that the electron had to overcome really were the ionization energy, this would absolutely never happen. Of course, I'm telling you about Marcus's theory of electron transfer because it was an important enough process to describe theoretically. For context, in a 0.1 molar solution, the ferrospheric exchange that we just described happens about 10 times a second, or with a characteristic timescale of 0.1 seconds. So clearly still a rare event. Relative to internal dynamics of the atoms and molecules that make up the system, the vibrational modes or rotational dynamics of a water molecule, even diffusive dynamics all occur on kind of picosecond timescales. There is a significant separation of times between those local relaxation events and the seconds timescale over which this reaction will occur. So clearly, there is a separation of timescales. The electron transfer event is rare. And so the insight that Marcus had was to develop the right reaction coordinate over which to project this dynamics and thus compute the relevant barrier that the electron had to overcome in order for that event to be, the rate of that event to be estimated. Indeed, this was not only was it foundational in that it came to underpin a lot of how we think about rates, especially those that involve charge transfer, but also was significantly innovative in how Marcus intuited a collective coordinate to project that reactive event upon. For this reason, Marcus was awarded the Nobel Prize in 1992 in chemistry. And so it's worth kind of going through what his thought process was in attacking this problem. So clearly, there's something special about, so if I really was going to take this electron and move it from an iron center to one iron center to the other in vacuum, this does not actually ever happen. You have to put an incredible amount of energy in the form of a laser to actually get this to go. So something is actually special about the fact that this process is happening in a polar solution. So let's actually draw some cartoons for what this actually looks like. So let's imagine we have our ferrospheric couple, we have some 2+ state here. And in its vicinity is the 3+ oxidation state. All right, well, first, that 2+ has an electron, which we all know now you can think about as a path. So there's the path. From the perspective of the water, what does the water see here? So I have a difference in charge separated by some amount of space. That's a dipole. Water carrying a dipole will react to the electric field generated by this charge distribution and polarize. Somewhat abstractly, like so. If the tables were reversed, and rather than the electron being on the left-hand side, it was over on the right. Oh, bummer. Shouldn't have put those 2s and 3s. So now let's put that electron over here. Now what must the water want to do? At equilibrium, the water would polarize in the opposite direction, aligning with this new dipole. Just thermodynamically speaking, if we wait long enough, that's what we should expect to see. So now note, in addition to the electron moving from one nuclear center to the other, there's a significant reorganization of the water. So let's think about that. So first, we've denoted where we've thought through what the characteristic timescale of that electron moving would be. That's something like attoseconds. What is a characteristic timescale for the motion of the water? Well, to reorganize, to repolarize in one direction or the other, requires that water molecule to relax orientationally. Typical reorientational time for a water molecule would be order picoseconds. Maybe tens to really get the full Debye relaxation of that dielectric. So nuclear motion is occurring on significantly different timescales than this electronic motion. Now, with that polarization comes a solvation. There's a favorable energy associated with the water polarizing in the direction which lies along the dipole generated by this charge imbalance. So energetically, there's a stabilization energy associated with that reorganization. Now, Marcus's real insight was to acknowledge that those two realizations, the fact that the water relaxes on orders of magnitude slower timescales than the electronic motion. If the characteristic timescale were picoseconds, that's 6 orders of magnitude slower than the attosecond timescales for an electron transfer. in such a case where motion occurs on two very different sorts of timescales, and if the electron were to be transferred from one side to the other, there's an accompanying solvation energy. So there's a change of energy, at least at long times after that relaxation event would occur. The only way to conserve energy in the electron transfer event itself, to move the electron from the left side to the right side, from one ion to the other, would be for it to happen at an instance where it was equal energetically to be on the left or to the right. So from the perspective of the electron, if it's going to be on that red center or the blue center, it essentially is moving so much faster than the water, it can't exchange energy with the water. And so only if it is equally energetic to be on the left or the right will it be able to move and conserve energy over the course of that dynamics. The separation of timescales results in a non-adiabatic dynamics, a dynamics over which only if in resonance with those two sites can the electron transfer event occur. So for example, if we took our red metal center and our blue metal center, we're imagining that those don't really have meaningful internal degrees of freedom. So if the electron was to hop from one side to the other, it would have to do so in an environment where localizing on the left or the right was equal energetically. And if what is tuning the energetics of one side or the other, they're both, in this realization, they're both water, they're both iron atoms. So the electron, from the perspective of the iron, is equal energetically, absent any environmental effects. So what we're waiting for then is an environmental fluctuation, a fluctuation in the surrounding polarization of the water that doesn't favor one side or the other, but establishes a resonance between the two sides. So again, in the case of the electron transfer, it's really the slow solvent configurations that must admit the same energy for the electron to be on the left or the right, provided that there is no ability for the electron to meaningfully exchange energy with its surroundings, due to the fact that there is such a large separation of timescales between those two degrees of freedom's motion. This is essentially the Frank-Condon principle that separates generically electronic and nuclear motion. Indeed, Marcus came on the scene right after Frank and Condon had established this principle. So again, just in order for the electronic transition to conserve energy, the energy for having the electron on the donor or the acceptor on this red site or the blue site must be the same. So then Marcus's insight was to then imagine that the relevant reaction coordinate our Q variable is the energy gap generated by the solvent, modulated by the solvent, between the electron being on the left or the right. More generally, between some donor, like the red, and some acceptor, like the blue. Let's denote that delta E. Okay, so that's the insight. That's the basic idea, that what we really wait for in an electron transfer event is a collective fluctuation of the solvent that makes that electron transfer possible. Indeed, in fast, slow systems and systems with very distinct timescales, it is always the slow motion which is going to gate a transition. Okay, to make things quantitative, we require a Hamiltonian, something we can actually manipulate, whose statistics we can understand. So a generic form for a Hamiltonian for the system would be a Hamiltonian for the electron, a Hamiltonian for the surrounding polar environment, some back Hamiltonian, and a coupling between the two. So the electron Hamiltonian is simple. From the perspective of the electron, it's just a two-state model. Either the electron is on the donor, the red center, or the acceptor, the blue. In general, the donor and acceptor energies need not be the same, so we can reference the energy of the donor state, say, to be 0, and the acceptor state to be some delta E. If there were no couplings between this two-state system, there would be no possibility to transfer, so there must be some tunneling matrix element that will connect the two. Mathematically, this is some outer product with 0 energy in the A states, delta E energy. Yeah, let's call it B. In some other states, and some coupling that is Hermitian. So in the ferrospheric case, that delta E is 0. If I pulled the electron off of the ferrous, I have 2 iron 3 pluses that I should have equal energies residing on either. But in general, we might have mixed metal centers or more complicated donor acceptor complexes where there's an energetic driving force to be on one over the other. So that's what delta E is meaning. This K, that's some electronic coupling that allows for that transfer to occur from our Hamiltonian at some matrix elements between A and B. Typically, it has the form of some constant, say K naught, and will depend on how close spatially A and B are from each other. Essentially, the picture is that this is from some electron overlap. If I draw my two species again. If the electron is over here, ooh, that's terrible. Let's move that center. There's some distribution of electron density. Analogously, there's some distribution of electron density if it was over there. That overlap is essentially what's giving us the tunneling element for the electron to move between the two. More specifically, if this is some R, and this is the location of RA and RB, there is some potential given by a Coulomb potential that electron is tunneling out of. So there's some tunnel splitting associated with that Coulombic potential that the electron moves in. And as the decay of wave functions are asymptotically exponential, that's why we would expect to be it exponentially decaying as the donor and the acceptor, the red and the blue, get further apart. The typical scale for these sorts of things are that this rate of decay is typically about an angstrom. So atoms in the two metal centers can't get too far away from each other. The typical size of closest approach, the sigma, is maybe about a nanometer. Essentially because ferrous and ferric metal centers are strongly coordinated by water, they can't actually get too close to each other. So in fact, this K, this coupling, this matrix element, is actually quite small given its exponential scale. If we actually knew K naught, which through measurements we know to be about 100 inverse centimeters, relative to the EV sorts of scales we're talking about for moving the electron around, we should expect that this K is a weak coupling, that the electron really is local, that consistent with the idea that the electron really becomes localized on one side or the other. If K was really large, the energy eigenstates of that electron Hamiltonian would be delocalized, which is not really the case here. All right, so now that's the electronic bit of the Hamiltonian. What about the bath? So the bath we're envisioning is modulating the energy of the electron through some polarization, through some electrostatic fluctuations. So from the perspective of the solvent, what Marcus did in his original theory was to imagine that the bath really was a continuum, that its fluctuations could be described through the continuum mechanics of dielectric fluctuations. essentially that they are a continuum set of dipoles that can polarize in response to an electric field. So if I thought about taking a object with size sigma in a, so let's imagine it's one of our species. Before it's charged, the dipoles of the water are oriented randomly. If I charged that ion, there would be a corresponding polarization associated with that electron. Say, imagine that I add an electron there. The dipoles are going to orient to be parallel to the electric field generated by that charge. And there will be a corresponding change in energy associated with that polarization. So let's let M be the dipole at some position R. The average dipole at R has a linear response relationship to the field acting on it. It responds linearly to a field, say, due to a localized charge with a constant of proportionality, let's call alpha. This alpha is the polarizability. And that's the field. So the electric field due to an ion depends on the magnitude of that charge. It's a vector, centrally symmetric. If I put the ion at the origin, it decays like 1 over r squared. That's just Coulomb's law. This is a linear response relationship. So alpha is how the dipole reorganizes in response to that field. The corresponding energy change associated with polarizing a dipole, if that dipole really acts like a within linear response, so it exhibits Gaussian fluctuations, the change in the energy can be computed so the energy or the potential felt by the electron due to the polarization field generated by the ions, or by the dipoles, excuse me, is minus Q, the dot product of that dipole field. It goes like Rj squared, that's the potential at J. The size of the dipole that is generated due to that ion, or due to the electron, that charge, goes like alpha Q squared, another factor of R, so that's Rj to the 4th. Integrating overall space, so computing the whole energy stored in the dipole field, will give us some delta U. Don't need to introduce these J's. up to some volume, to the energy density. It's radially symmetric. Can integrate up to some size of closest approach. And that integral scales like q squared and inversely proportional to the size of the ion. So to go back, so if I take a solution, charge an ion, I will generate a polarization from the dipoles. That polarization of the dipoles will act back on the ion with a favorable potential. There's an ion field potential associated with that dipole field. It itself generated, that's known as a so-called reaction field. The size of the dipole field generated by the ion's electric field within a linear response is proportional to that field with a constant proportionality, the polarizability. The back reactive potential acting on the electron, so the electron self-energy, then is a field dipole energy integrating over that whole space to the energy stored in the dipole field gives us something proportional to q squared, the charge of the ion, and inversely proportional to the size of the ion that the electron is residing in. This is known as the Born solvation model. And is discussed in some of the extra set of notes that I have I think I've posted on B courses. If you're really interested in dielectrics, you can go and read up more about that. Turns out that this polarizability is related to the dielectric constant of the medium. So this delta U could be rewritten in terms of a difference in dielectric constants. In this case, the static dielectric constant. For water, this is about 80, reflecting the fact that the charge generated at the surface of the dipole due to that polarization is nearly a full charge. It's nearly a perfect conductor. For an ion that's about a nanometer in size, this gives us about an EV of solvation energy. Okay, so this is to say that we can, that's the kind of basic energetics of the field modeled through a polarizable continuum. So HB is some function of all those dipole fields, some Rn degrees of freedom, whose fluctuations we can characterize just by the electric fields that they impose on our electron. So putting these two together, so we have our electronic Hamiltonian in this site basis of the donor and acceptor. We have electric fields generated by the solvent that occur with different orientations depending on whether or not you're pointing the field in the direction of the donor to the acceptor or vice versa. And then we have some Bath Hamiltonian that tells us how those electric fields are fluctuating. But that is diagonal in the electronic state spaces. So a way to rewrite this is that there is some fluctuating energy on the acceptor A side. There's some fluctuating energy due to the fluctuating fields on the B side. And we have these couplings off diagonal. This puts us in a position to actually write down what that energy gap is. It is an explicit function of the nuclear coordinates of the solvent given by, defined as HA less HB, but given by minus twice the electric field, the polarization generated by the dipoles of the water, less some energy offset that might tell you that one site is more favorable than the other. So that is the energy gap. So the probability of having where the energy gap is 0, that's our transition state. That's where it would be equal energetically to move the electron from the donor to the acceptor. That is given by the probability to have an electric field which is equal to minus delta E by 2. The initial offsets. If the two species are the same, so in that ferrospheric case, this would be just the probability to have no net polarization. But in general, if there is a bias, there is some counter polarization that offsets the energetic bias. So the probability of a given polarization from the surrounding solvent, this is occurring autonomously without any energy injected, so it is given by a Boltzmann distribution. And thus one needs only the free energy to create a given polarization of some magnitude to know what the probability is. Within dielectric continuum theory, within that linear response approximation we briefly alluded to, that free energy can be modeled as a Gaussian with some constant of proportionality that tells me the extent of fluctuations known as 1 over lambda, so-called reorganization energy. So for an electron localized on site A, we have our unperturbed Gaussian distribution of the polarizations plus some polarization oriented in the A direction plus some energetic offset. Oh, no, sorry, this is a minus, no offset, we put that in B, for it localized on B. We have some Gaussian distribution, point that field in the opposite direction, and have some energy offset. So our criteria then for the transition state are where these two parabolas intersect. So if we were to plot these, we have some Gaussian distribution, another Gaussian distribution, say for delta E is equal to 0. If delta E is equal to 0, the transition state lies just at 0. So the fluctuation that we wait for is a fluctuation that puts the polarization to be net neutral, to not be pointing in either direction. In general, even if there is an offset, where those curves cross are where the energetics of the electron transferring is resonant. So we can solve for the location of the transition state by setting FA is equal to FB. That defines a value of a field or a free energy barrier, which is equal to delta E plus lambda quantity squared over 4 lambda. We actually solve for that. We can do that. Let's go ahead and do it. So if these two are equal, the quadratic pieces cancel, or we already know we're just evaluating this at delta E over 2. And subtracting off its 0 value. Okay, whoop. Let's put this stuff down here. Let's jump in the gun a little bit. Okay, so that's the transition state energy. Note it's quadratic in the driving force, delta E, and quadratic in an offset of that driving force, this reorganization energy, this characteristic scale of fluctuations, lambda. If you compute from dielectric continuum theory an approximation to lambda, turns out that a good approximation to it, that's the characteristic scale of fluctuations, is given by the difference in the optical dielectric constant less its static value. This is because one can relate the curvature of these parabolas, if these parabolas have the same curvature, to the vertical excitation energy. This curvature, 1 by lambda, turns out to be the same as the vertical excitation energy at delta E is equal to 0. And thus, free energetically, I'm taking an electron that's solvated by a polarizable media, and I'm exciting it to be instantaneously delocalized across the two. They're the only ability to solvate the electron comes not from the slow static modes of the dielectric, but rather by the optical modes of the dielectric. When lambda is equal to minus, or when delta epsilon is equal to minus lambda, I'll have the smallest free energetic barrier. Okay, but with all these together, so we have the probability of finding this resonance condition. To turn this actually into a rate, we can go back to transition state theory, or in the quantum context, Fermi's golden rule. The rate of electron transfer in Fermi's golden rule, assuming that coupling between the donor and acceptor states is small, we can use that as our perturbation, have that matrix element squared, and Fermi's golden rule insists that we conserve energy. In this case, that the energy of being on the donor or the acceptor has found a resonant condition with the bath. Now, those energies fluctuate due to the fluctuations of the bath, so this is a thermal average. So that matrix element we've put in by hand, that's our K. We get it squared. And now I'm just looking for the probability that I find a delta E is equal to the energy of the bath. That's what we just worked out. That is e to the minus beta, the energetic offset, plus that reorganization energy squared over 4, that reorganization energy. If I were to normalize that distribution, I would get a factor of pi lambda over beta. So this is our transition state theory estimate of the rate of electron transfer. It's the probability of getting to that transition state. Now we find that the attempt frequency is just given by that tunneling matrix element K squared over h bar, up to factors of 2 pi. So what plays the role of a thermal flux and in a quantum mechanical system is really a quantum flux. That's the flux through the barrier, and this is the probability of reaching the transition state. In this case, given by that resonance condition, probability of finding the particle, the electron, finding the solvent in a configuration where the energies of the electron being localized on one side or the other, the donor or the acceptor, is identical. So this is Marcus's big result, a rate, an explicit formula for the rate, depending on a driving force for localizing the electron on one side or the other, this delta E, and a reorganization energy, lambda, also simply computable within a dielectric continuum approximation for that characterize what the extent of polarization fluctuations are in a polar medium. Now, if you look at that rate, there's a non-trivial dependence on delta E. So if you were to, say, plot the free energy of the energy gap, let's set one of those at 0. And take the other with the same curvature, but that has different energetic offsets. So we could start it, say, here, no energetic offset. We could give it some energetic offset in the positive direction, decrease it some more, or decrease it even further. Now we need to continue our axes. This has gotten a little complicated. Let's make this a different color. That's our one state. Those are different states. So these are different values of this delta E, making the donor states, or the acceptor states, call this FB and this FA, more and more favorable. So the electron is transferring from here over to here, one of those states. So now look, the barrier is where those two curves cross. And as I decrease, if I forgot about this one for the moment, as I increase the energetic offset, the driving force for stabilizing the electron transfer event in the B direction, that barrier gets smaller. I come here, smaller values. But now look, if I made that B, that acceptor state, really favorable, well, that barrier passes through 0 and starts increasing again. So indeed, the prediction from Marcus is that the log of the electron transfer rate as a function of that driving force, the thermodynamic driving force to localize on the acceptor states, is non-monotonic. The rate starts to go up as I make the acceptor more favorable, but then turns around and it becomes, the rate to transfer becomes smaller and smaller as I make the state that it's going into more and more favorable. Our intuition, I think, is normally to expect that if you make the product state stable, you will increase the rate of forming that product state. So you call this side the normal regime. A non-trivial prediction of this specific form of the transition state from Marcus theory is this so-called inverted regime, where the rate decreases with increasing driving force. So this is the prediction. If you go in and measure it, the normal regime is well described, and indeed, there is a turnover. That's what I was actually showing you here. This is foundational set of experiments in an intramolecular electron transfer event from Miller, Klaas, and co-worker, where they studied a system of conjugated polymers, conjugated molecules, and studied the intramolecular electron transfer event. This one in particular is a little bit better than typical ferrospheric electron transfers, showing that indeed there is a turnover in the rate as I increase the driving force for the electron transfer. This experiment was done 25 years after Marcus's initial prediction of the inverted regime. And essentially directly following it, he was awarded the Nobel Prize for his result. So this confirmation of the confirmation of a non-trivial prediction of his theory is what really gave him what was the prize was awarded for. Most cases, there's a deviation here. So in the Ferrospheric case, one actually sees a deviation quantitatively between Marcus's prediction and data. So this is data. And that has to do with the fact that we've treated the solvent as a continuum and specifically not quantized its fluctuation. So not only is it a continuum, but it's a classical continuum. Turns out quantum vibrational fluctuations tend to increase the rate in the inverted regime. All right, well, okay, so that's really what I wanted to tell you about Marcus's theory, to kind of reflect back on what we did. So we have in our hands the tool of transition state theory, which is exciting and really useful in that it prescribes the rate of some rare event, of some reaction, based solely on thermodynamic or structural properties. One needs a flux, a characteristic flux over a barrier, and the probability to reach that barrier. But hidden in that simplification is the identification of the relevant barrier that you're overcoming. In Marcus's theory of electron transfer, what he argued was the right reaction coordinate, the right description of the dynamics, is one in which the rare bottleneck was described not at all by the electron itself, but rather by the slow motion of a solvent, which tuned the relative energetics of the electron on one side or the other, associating some simple properties of that environment, like its linear response. It being a continuum dielectric, one can work out then an explicit expression for the transition rate, given here as a product of the probability of having a specific fluctuation of the polarization that makes the donor acceptor state isoenergetic. And in this case, using Fermi's golden rule to estimate the flux, one sees that it's proportional to a tunneling matrix element squared over h bar. And that this actually works. So Marcus theory is quantitatively accurate in a number of cases. All right, so that's all I wanted to really tell you about today. So we can wrap up. In the next lecture, we'll spend one more lecture on reaction rates and rare events, thinking about generalizations to where a reaction coordinate is not easy to intuit. So what do you do then? And how do you move to bimolecular rate processes? And following that, we'll really switch gears for the remainder of the semester and focus on nonlinear static phenomena in the context of phase transitions, and specifically the Landau-Ginzburg theory of phase transitions. So that's where we're heading. So I look forward to seeing you all in the small groups, and hope you're all well.